Since we've already talked about hypothesis tests, we're also going to look at conducting hypothesis tests to determine whether there's a linear correlation. Now these tests are a little bit easier because we don't have to do very much work to come up with our null and alternative hypotheses. For linear correlation tests, the hypotheses are always like this. The null hypothesis is that capital R equals 0, saying there's no linear correlation. The alternative hypothesis is that R is not equal to 0, and that implies that there is a linear correlation. Our test statistic formula for this hypothesis test is T sub 0, and notice that the T here means that we're using the T distribution. The R in here is the correlation coefficient, so we have R over the square root of 1 minus R squared over n minus 2. N is the number of data points that we have, so it's our sample size. Let's do an example. If we go back to our study on colas and bone mineral density, we found that the correlation coefficient R for the sample data was negative 0.806. We're going to use that to conduct a hypothesis test of the claim that there's a linear relationship between the number of colas drunk per week and the bone mineral density in women. So step 1 is to write our claim. This would be that there is a linear relationship between the number of colas drunk per week and bone mineral density in women. We're going to translate this into our alternative hypothesis. This part's easy because it's always going to be the same. So our alternative hypothesis is that R is not equal to 0, or if we want to put it in words, it would be there is a linear correlation. Our null hypothesis is that R is equal to 0 and there is not a linear correlation. For step 2, a type 1 error here would be supporting the claim of a linear correlation when there actually is not one. If we say the consequences in this case are somewhat serious, we could set our significance level at 0.05. Alright, for step 3, we're finding our test statistic, so we're using this formula to calculate it. The R from our sample was negative 0.806, our sample size was 15. So here's our calculation by hand of our test statistic. We get negative 4.91. In what we did to get our linear correlation coefficient, it also showed us this information. And what we're going to look at for this is where it says slope. So we want to look at the slope row of this table, and notice it gives us our t statistic, which is very close to the one we came up with. We had negative 4.91, and this is negative 4.903, and this gives the p-value as being 0.0003. Our next step is to compare our p-value to alpha and get our initial conclusion. Our p-value is 0.00028. Our alpha was 0.05. So our inequality looks like this, and this is a true statement since this value is less than or equal to 0.05. So we're going to have a positive conclusion, which is reject the null hypothesis. For step 5, we'll also have a positive conclusion, and we just write it out in a sentence. So we would say there is sufficient evidence to support the claim that there's a linear relationship between the number of colas drunk per week and bone mineral density in women. Now remember with all this that the methods we're learning in this section apply to a linear correlation. Even if we conclude that there doesn't seem to be a linear correlation, remember that it's possible there might be some other association that's not linear. Let's look at another example. A study was conducted at a hospital suspected of inflating charges for older patients. Data was collected for a sample of 30 patients with similar diagnoses with the following results. So we have our summary statistics for charges and patient age, and here are our simple linear regression results. So notice down here our correlation coefficient comes out to be 0.194. And now we're going to use that to conduct a hypothesis test of the claim that there's a linear correlation between patient age and hospital charges. When we do that linear regression on StatCrunch, it also gives us a scatter plot, and it goes ahead and draws a line in there. So here's what our scatter plot looks like. Now the test statistic for this test turns out to be 1.046. The p-value is 0.3045. Since this is a large p-value, it will not be less than or equal to alpha. We'll have negative conclusions. So our final conclusion for this would be that there's not sufficient evidence to support the claim of a linear correlation between patient age and hospital charges. So now let's look at some common errors involving correlation. Number one, even if we do find that there appears to be a linear correlation between two variables, that does not mean that one causes the other. So correlation and causality are two different things. Another common error is using averages. Averages tend to suppress individual variation, so they might inflate the correlation coefficient. And third, there might be some relationship between x and y, even if there's not a linear one.